thank you all for coming. It's great to be here. I always enjoy making a trip out to Berkeley. I have to say, I go to Stanford and I go to Berkeley, and whenever I come to Berkeley, I remember what the 70s were like, and I enjoyed the 70s, so I'm glad to be here. The genesis of this talk, I'll tell you, really was putting together a plenary talk for IROS last fall. When I was doing that, I started to think about what I thought some of the themes of my research had been over the last 20, 25 years, and kind of how they came together. And so particularly, I would say for the grad students in the crowd, this might be a way to think about the fact that right now you're kind of deep down in your thesis research, and you're just hoping to kind of get past that first hurdle of finishing your dissertation and going on to do something. But hopefully this will give you a sense that there's a much broader arc to what you'll do than that. Certainly, as I went back and put this together, it was kind of fun to see where some of the key points were. So this is going to take a little bit of an historical perspective on the work I've done, and then kind of try to tie it together at the end. So the title, From Mimicry to Mastery, well, so it really kind of starts from the point of view that I got to turn on my clicker. That right now we are obviously in a real golden era of robotics. There's no question that in my lifetime I have never seen so much excitement, so much visible interest, and so much progress in robotic space. But it's still the case that when you think about all of the different robots that are being deployed, they tend to be extremely narrowly focused on a particular application, like mowing your lawn. And I doubt that you would say that any of these robots are a world master at what they do. They maybe suffice to solve a particular problem, but we still kind of think of robots as, or our research really as, okay, can we get it over the bar of being reasonable, as opposed to saying, really it can master something. And so the theme that I'd like to think about, and kind of the challenge that I'm thinking about in my research, is what would it take to really create systems that are able to master a particular set of activities. And this, for me, is obviously inspired by the fact that I've done a lot of work in medicine. In particular, I've worked a lot with surgeons, and surgeons really are a master at their craft. And it's a unique craft as well, because it's a craft that requires both a lot of cognitive ability. You have to know a lot of things. You have to have also a lot of experience and background. And you have to have a lot of physical technical skill. You have to be able to manipulate the world quite well. So it really brings together all these threads of being a master, understanding background, experience, and technical skill. And the key thing here that I'm going to kind of focus on ultimately is, what does it mean to be skilled? Because I think really what mastery means is it means achieving a high level of skill at a particular task. And that's the thing that I think right now we really, if you think about where robotics needs to go, we need to start to think about what does it really take to create robots with very high capability, with very high skill. So a lot of the theme I'm thinking of is, what's the path for robots to become skilled, and how do we get them on it? So I said I was going to take a little of an historical perspective, and really the kind of beginning point of this talk goes all the way back to 2000. It was an ICRA talk I gave, a paper we published. These are literally, almost literally, the slides from that talk, where I was doing a lot of work in visual servoing at the time, so control of robots using vision. So we had real-time vision working, and we had new methods to control robots using vision. And I realized I could do all these really interesting tasks, except I really had to construct the tasks kind of laboriously by hand, literally writing kind of C code like this. And so when I gave this talk, I said, really, I don't want to program robots anymore. I want to make robots useful by being able to describe tasks to them in some form and having them be able to elicit the information they need to abstract from the world to perform that particular task. And then, I kind of proposed a little programming paradigm for doing this, where, it talks about finding objects and then doing things relative to objects. So all the red stuff is, well, find me something like a screw or a screwdriver. But then also, there's a lot of object knowledge here, like, the tip of the screwdriver is the thing that actually acts on a screw, and you need to bring them into contact. So a lot of the implicit inference that you do in your head when you're performing a physical task really was very much explicit in these programs. And so kind of going through all this, I said, well, look, what are the things we need to do to be able to make this a reality? For me to actually be able to go into my workshop, to have a robot there, to be able to demonstrate some tasks to it, and to have it collaborate with me to build something in the workshop. And the shtick at the time, I'll tell you, is my son was about 5 years old, and he was just starting to help me in the workshop. So I said, well, look, you know, my son is 5 years old. He's starting to help me in the workshop. I've got him for about another 12 or 13 years. So we have 12 or 13 years to get a workshop assistant that I can bring in, because he's going to go off to college, and I need him by then. Well, suffice to say, he's in college right now, and I'm still looking for that assistant. But I think we've actually made a lot of progress. And so what I'd like to do is talk a little bit about some of the progress I see, both in my own lab and more broadly, and then maybe some of the more open-ended side of things. So first, to talk about the progress, you see the first half of this list, and this is literally the list from that 2000 paper, was I said, well, we need all of this perception stuff. You know, that program had to be grounded in the real world. And yes, I can track objects all I want, but it assumes that me, the person, finds that object and kind of wires up something that allows it to be tracked. So I need all of this being able to structure the world so that my program can be grounded, and then I can build on top. Well, you know, suffice to say, over the last 15 years, there's been tremendous progress in computer vision. If you look, though, at the progress in vision as a community, while it's been tremendous, it's not actually vision that's particularly actionable for robotics. So, for example, a pretty typical vision task is I'll give you a photo, and your job is to draw a bounding box around some object that you know and label it. And that could be you know, useful for a robot to see that there's a bicycle here, but if you actually wanted to manipulate that bicycle, you need to know a lot more about it than just the fact that it happens to exist in an image. And in fact, I had a student, Che Li, who kind of took on this challenge. And what I did is I coupled him with another student, John Boren, who's more of a robotics person. I said, look, you guys got to figure out how to work together to make perception work for robots. And the sort of task that we were thinking about was something like this, where I give you a bunch of parts, and your job is to build a structure out of those parts. So kind of a you know, simplification of my workshop scenario. And it turns out that if you take you know, any sort of CNN, RNN, VGG, pick your favorite vision technology, it actually doesn't work very well in this sort of a scene. That's just not its design space. And in particular, it won't tell you things like really how many parts are there, what are the poses of those parts, the information you would need to actually declutter that pile and then actually build things. And so that was the challenge I gave them. So they got together, and in the end, they have a pretty simple idea, which is to say, look, the vision front end is pretty good at giving me hypotheses of things that are out there, you know, the bounding boxes effectively, but it doesn't give me the back end I need, which is the real-world geometry. So let's just couple those two together. Let's try to come up with a really efficient architecture that can build lots of hypotheses using semantic segmentation of objects. But then the back end will use some sort of a 3D model basis to actually register them, compute poses, and verify identities. And this all assumes RGBD data, because in robotics, I'm perfectly happy to assume I've got a depth sensor. Yes, the real world likes to upload 2D photos, but you know, a robot, there's no reason it can't just carry around depth as well. So this is just a kind of quick synopsis of the results we're able to get. So these are some cluttered tool scenes, kind of ever more cluttered. You can see the key thing here is we're getting a lot of very similar tools. So again, we want objects that are actually really representative of the real world. They're not, you know, a baseball and a car and a bicycle. Those are pretty easy to tell apart. And the scenes themselves are kind of the typical thing you would see if you jumbled a bunch of things together. And we're actually able, through this now, to get you know, north of 90% recognition rates on objects. And in fact, if you go to each scene and say, look, I just want to find the topmost object, because there's almost always a topmost object that's not occluded, almost 100% of the time we're getting correctly the pose and identity of that object. So this is just a way of saying, you know, that first part, can you find objects, and can you now kind of map objects to what I'll think of as their affordances, really is practically doable. You know, we can build technology that does that in a quite reasonable way. And in fact, then we married that up with some work that my student Kel Guerin was doing on robotics for manufacturing, where we wanted to build collaborative robots. Actually, it's part of an NRI project with Ken and Peter, Alison Okamura at Stanford, Blake Hannaford, and Jacob Rosen. And to make a long story short, Kel created a very handy little perception-grounded programming environment, basically a capability-based programming environment, that allowed us to very quickly throw together kind of interesting little programs. So this is now my workshop assistant incarnate. So Kel is sitting there drilling, and it recognizes the drill, and it sees, well, OK, there's a drill there. I better move the vacuum over to clean up the shavings. Or down here, you're working on a part. So my workshop's a mess. Like, I'm awful at putting stuff away. And so this is the robot I actually need, which my son never did, which I leave the tools behind, and it's able to detect that there's a tool being left out. It recognizes the tool, knows the pose, knows how to pick it up, and handily puts it away. And the key thing here is this is almost turnkey. Like, this was, I emailed them a couple days before the talk and said, hey, guys, could you throw a couple demos together? And the next day, they emailed a video of these demos working. So over that 15 years, we've really made a tremendous amount of progress on the perception side of things. Now, that's not to say it's solved, but it's certainly the case that we really have capabilities to build on top of. So the second half of my list back then was to say, well, OK, once I've got perception, I need to interact with this thing. If I'm going to have a workshop assistant by definition means that it understands things like what tasks am I trying to perform, what are the kind of standard ways to do it, where do I need help, if I put a screwdriver down here, do I want it put away, or am I just going to use it again at the next step? So a lot of it was much more about how do I teach the robot what it is I'm doing, and how do I interact with it in a way that's reasonable. Yeah, Peter.
For the perception, is it instance-based perception or category-based perception?
Instance. So that's instance perception. And for most of what we're thinking about, we're assuming that you're in an environment where you know your environment. It's not that you are going to be confronted with a new drill every day that you somehow have to learn how to do. Do you know how to do category? No. I was hoping. No, it's instance-based for sure. So let me. So the idea here really that started to be, well, to do the second half, I need to interact with people. I have to learn from people somehow. And so the rest of this talk, a lot of it is going to be what we've been doing in the last few years, trying to understand how it is that people perform complex tasks and how eventually we might be able to learn from people. So the starting point of this is really when we started the center at Johns Hopkins that Ken mentioned. Intuitive Surgical started at about the same time as a commercial entity. So fairly early on, we were in discussions with them, and we started to get access to some of their technology from the Da Vinci robot. Now, the key thing about the Da Vinci, from our point of view, is not so much a surgical robot. That's great. But it is a surgical robot coupled to a person who is performing a really interesting and complex manipulation procedure. And furthermore, because it's got a computer now between that person and the procedure, that means that we can record data at scale. So we actually build a recording box that goes into a Da Vinci. It pulls all of the hand motion data. It pulls all of the video data, couples all that together, and essentially drops a complete record of the surgery. Every bit of motion that went into the patient, every pixel that came back out of the patient. And in principle, you can now do this at interesting scales, so upwards of 1 million procedures a year. So if you think of what uploading photos did to computer vision, this is really kind of the opportunity space for understanding how people perform skilled tasks. You can now get data at a scale that allows you to study manipulation in interesting ways. So we basically started to look at this, and we essentially posed the question of, well, if we can get this data, this means we can study manipulation, but we can also study the learning curve of manipulation. That is to say, we can start to understand what does it mean to be a skilled surgeon. So kind of going back to my opening slide, we can actually start to get our hands on what is skill, what are the signatures of skill, and how can we start to understand what it would take to make a robot skilled. And the way to think about this really is in terms of this apprenticeship model that was introduced into medicine by William Halsted in 1889. So this is a model that was actually created in Germany, imported to the United States by Halsted and Ulsler, in fact. But it's called See One, Do One, Teach One. It's called the model of graduated responsibility. You start out watching a procedure, eventually you take over portions of the procedure, and finally you become a master and are able to perform the entire procedure, and at that point you teach the next person. And so we started to say, well, what would it mean to kind of take apart this learning model and start to replicate it, but replicate it for robots, to be able to first understand procedures, eventually start to take over pieces, and eventually do the entire piece. So the first question we had, though, is can we actually structure this data in an interesting way? Now, the way that we have kind of phrased this is really, we have to get buy-in from the medical side. So we basically say to them, can we build analytics that will make you more skilled? Which means, again, we have to be able to recognize the elements of skill. Now, it turns out recognizing skill is not as hard as you might think. I'll give you a little test if you haven't seen this before, which we'll probably show that to you. There's 2 performances synchronized of an expert and a novice performing a 4th-row suturing task, which I'm going to run. And I'll let you watch for just a second and see if you can decide who is skilled and who is unskilled at this task. One is an attending surgeon, and one is actually somebody who knows surgery. They just haven't used the robot much before. So I think you probably already are kind of guessing, but we can let it run for a little longer. You never know. Something might happen. OK. 1, 2, 3. Got it. OK. Now watch one other thing, though. So now they're pulling the suture. So they pull the suture. With obviously the expert on the left, adjusts the needle a little bit. Notice that the hand across actually is just about the same speed. And that's because that's a pretty easy thing to do, right? And then you go back to driving the needle. Now that's what you see, and obviously you could tell the difference pretty quickly. This is what the data says. So this is actually a recording of those 2 people doing that procedure. You can see there's 1, 2, 3, 4th rows. The expert does well. The novice is actually getting the task done, but you can see there's much less organization in the data. And that's really the signature we're looking for. We can actually start to use this data to look for that sort of spatial organization as a way of assessing skill. And in fact, another way to think of this is there's these component actions that you can think of doing, like you drive the needle, then you pull the needle, then you pass the needle across, and then you reset, and then you drive again. You do it over and over. So there's a very small vocabulary of actions it takes to describe this task. The color coding here actually is that a hand labeling of those component actions on both sides. And if you actually write down the state diagram, you can see here's the expert, the very linear, very organized, very efficient. Here's the novice going back and forth, making mistakes, repeating, backing out, and doing it again. And so, in fact, if you just take these sorts of diagrams and you do a dimensional reduction, you immediately start to see a skill space emerge where novices appear over here, and then they kind of pass from novice to intermediates and eventually up to experts. So we really can, from this data, start to see some of the signatures of skill. And I'll show you more examples of this as we go on. So this was the genesis of what we call the Language of Surgery project. Really, it's 3 problems: recognizing what's going on, recognizing the quality of performance, understanding the signatures of skill, and eventually what we'd like to do is to also provide feedback. Because providing feedback means, when you can teach something, you understand it. And so if we can provide feedback, it means that we can provide feedback to a person. We could also provide feedback to an automated system that's now trying to improve its performance on that task. So let me just give you kind of a couple snippets. We've been working on this for a while now. We just had some recent publications that are going to actually come out soon, just to give you a sense of how close we are to actually being able to process this data. So this is mostly the work of Colin Leah, who's a grad student just getting close to finishing at Hopkins. He's also a co-author on a paper with Ken and Peter and Animesh and others. I forget who I'm leaving off. But we co-authored a paper actually on segmenting some of this data. So what Colin's been looking at is segmentation, meaning if I just give you a stream of data, can you break it down into those component actions reliably? So can you structure the data into those surgeons that I showed you? In the interest of making sure things generalize, he actually has been working on 2 data sets. This is kind of a general manipulation data set. It's called the 50 solids data set. It has accelerometers and video. And then this is what we call the Jigsaws data set, which is a set of training exercises from the Da Vinci, which has video and kinematics data from the robot. And Colin has, I think to date, the best performance we've recorded actually in both of these data sets. The way that he is looking at the signal-based data, so again, the kinematics and the accelerometers, is he's essentially inferring a set of latent action primitives. So for a single action primitive, like driving the needle, he'll let the system break it down into some smaller component actions. He learns essentially a convolution that responds well, a template that responds well to those component actions. Does that through basically a convolutional learning process. And then he drops it into a skip chain CRF that then does the time series linking together of those actions. So he basically finds some signatures, so he basically learns several convolutions, and then the skip chain CRF learns effectively a classifier and a time series model that allows us to put that together. So from sensor data now, we're actually getting up to accuracies that are in the mid to high 80s. And the way to think of these accuracies is it's saying, if I look at any given frame, how often am I giving exactly the right label to that frame? If you look at so here, for example, is the ground truth. Here is the skip chain CRF. You can, in fact, see that the CRF is doing pretty well. What it's really doing is it's just not quite getting the boundaries of the action right. But it's got a pretty smooth signature with just a few errors sprinkled here and there. And roughly the same thing for jigsaws. So we're actually getting kind of the right set of actions now. It's mostly getting the alignment of those boundaries to really line up well. And I should say this is 50 solids. Jigsaws is a little south of 100 trials. So we're nowhere near 1 million. And I suspect if we could simply scale this up by a factor of 10 or 100, we would actually see most of these recognition rates go up into the 90% range. Colin's also been looking at it from video. So one of the things I'd like to do is I'd like to be able to do this without having to tap into the Da Vinci or more generally if I were going to watch some other surgery where I don't have sensor data. So he's actually developed convolutional architecture for that essentially starts from video. It has a spatial unit that tries to eventually return a set of probabilities of each being in each phase. Separately, he trains a network that returns a set of attributes, like which tool is in use, whether or not cautery is happening, whether there's blood in the field, basically a small set of properties like that. And then that essentially feeds into the same sort of architecture where he learns a latent action model where he's got multiple sub-actions per, in this case, phase, each of which is then linked through a temporal model. And in fact, he's been applying this to live operating room data. So this is phases from video data. And we're getting on the order, again, of this is probably the most, actually, let's see, which one do I want to pull here? Tools, best attributes. Yeah, this one. So this is actually kind of our current recognition rate for this data. So this is taking an entire surgery. This is cholecystectomy. Again, labeling it by what actions are taking place, in this case, phases of the procedure. You can see we're getting about 80% accuracy in labeling. So literally taking data video data out of the operating room and saying, what part of the procedure are you in at any point in time? And all this really has come in the last 2 or 3 years, again, with a lot of the same sorts of things we've been seeing in computer vision, applying a lot of the deep net type architectures to this data. But it is realistic for us to now start to take these signals in this video and break it down into those component pieces and be able to do that sort of assessment. And since deep nets are so popular, I will say we have tried deep nets, and they actually do improve our performance slightly more. So we're actually getting about 85% on jigsaws out of some deep net work that we've been doing. But this is unpublished at this point, so don't believe it until you actually see it in publication. So that's just kind of a little bit of a background. I could do a whole talk just on the techniques we've used to break things down. The main message there is we can actually take this data and we can meaningfully chunk it into either component gestures, into maneuvers, which are kind of mid-level chunks of action or actual operative phases. And they all operate in about the 85, in some cases as high as 90% recognition rate. So if we've got the chunks, another question is, well, can we recognize the quality of performance of a particular chunk? So this is some work from my student Nargis Hamidi from a couple of years ago that we continue to rely on, where now what we want to do is we actually want to look at what's happening in a chunk and apply an actual skill assessment to that particular chunk, a particular maneuver. And the problem we were having is that when we get very carefully curated data from our training, we can actually do a pretty good job of recognizing skill just using those discrete state models. When we get more and more into the wild, like if we go into the live OR, those models aren't robust in terms of being able to identify quality of performance. So one of the things Nargis started to look at is, well, can I come up with a more invariant representation of the data and then mine something from the data directly? And so what she observed is we can essentially build a discretization of the signal where we set up a Frenet frame along the curve. So we now have a coordinate invariant representation of the curve. And then we simply record movements as a discrete set of direction changes. So I'm moving ahead, left, right, up, down, forward, backward, relative to where I currently am on the curve. And so this essentially turns that continuous motion data now into a string. And once we have strings, being a computer scientist, I like anything that's discrete. I'll get lots and lots of strings, that is training data from somebody performing the task. I can build a dictionary from that. So I essentially build a dictionary of motifs that occur repeatedly in a string for a certain category. It could be a gesture, it could be a skill level. And now when I see a new string, all I do is I say, what is the dictionary that was most likely to have produced that string? And I use a simple string kernel method for doing so. And in fact, if you do something like gestures, you can fairly quickly start to see separation between the different gestures just in terms of the prevalence of the strings that occur during the performance. And the neat thing about this is we turned this loose in the operating room. So what we did is we trained it in the lab. So you saw that fourth row running suture task. We actually trained this in the lab on that running suture task. So it had never seen live surgery before. It had only seen suturing in the lab. And then we took some snippets from laparoscopic hysterectomy, where they're doing a cuff closure, and they essentially do running suture. And roughly 75% of the time, it was able to distinguish whether it was an attending or a resident, a trainee, essentially, who was operating the robot. So it's not perfect. It's not something I would want to stake my, my career on at this point. But it shows that there really is signal out there and that these automated methods in live surgery can actually start to discriminate what sort of level of skill a surgeon is performing with. Just to kind of back that up with a second example, this is some work we did in a procedure called septoplasty. So septoplasty is what's called an index procedure in medicine. It means it's a procedure that every surgical resident must perform before they're qualified to be a surgeon. And this particular part of the procedure is it's raising what's called the septal flap. It's the mucus covering, or the skin covering of the septum of your nose, so right up in here. It's an interesting procedure to work on because you can see it's a very confined working space. The surgeons who are performing it have a line of sight where they can work, but the trainee can't share that line of sight because there's not enough room to get two heads in the same place. And conversely, if you're a trainee doing it, the attending can't see what you're doing. So there's this kind of funky training environment where you're trying to guess what they're doing based on what they're telling you and then giving them advice of what they should do and what they should be seeing and hoping that they get it. So we attach tracking devices to the tools. So kind of like the Da Vinci now, we're getting effectively kinematics of the tools that are coming out. So this is what a novice looks like doing septoplasty. Each of the nodes in this graph are a point where they're raising the flap of skin, and the connection between it is a spatial movement between the nodes. They start at blue, so they kind of work their way back, and then they come back on the red, releasing this flap of skin. And again, it doesn't take a lot to say, okay, this is a novice. They're not as organized as an expert who's obviously doing it much more efficiently in a much more organized fashion. It's not hard to build data analytics around this. So in fact, we tried a bunch of different data analytics. And here's what we found. So the canonical thing would be to say, well, look, we're getting a continuous signal. We'll just build some statistics on derivatives of the signals, so acceleration, jerk. That's a pretty common thing to do, in fact. And it's if we actually get to see a surgeon once before we have to classify, we actually do pretty well with this signal-based analytics. But if we've never seen the surgeon before, the signal-based analytics basically operate at chance. This is just a two-class problem. The DCC I just showed you, in fact, works at about 90% rate if it's had a chance to see the surgeon. It almost maintains the same rate ab initio. So if it's never seen this person before, it's still almost 90% accurate at recognizing if it's an attending or a novice surgeon. The HMM things that we showed you, so the discrete state model. Again, what we found is that it's just not really robust in the wild. So you can see it's running at about 60% here and actually almost back at chance over there. And then just to say, okay, how good could we do if we just by hand built the best thing we could? So we took the strokes that you saw and we built some analytics around strokes. And we tried to build just basically a very structured model, which, again, if it's had a chance to see a surgeon when it's training, does about as well as our DCC method. But in fact, in the wild, when you have never seen a surgeon before, it also suffers in performance. So in fact, these sort of data-derived methods, like many other areas of AI, seem to be starting to emerge as a fairly robust alternative, particularly as we start to get a larger and larger scale of data. And in fact, this once we fielded this, the surgeons who saw it were so jazzed that they could actually get data and analytics out of it that they almost refused to let us take it out of the OR after we had finished our R21. So that was good news. So we applied for an R01, which we got. We're actually building now a standardized data collection apparatus, which we're deploying in 5 operating rooms around the Johns Hopkins hospitals, with the idea that we're now going to see if we can actually scale this out into a real data analytics platform for surgery. And there's, again, another whole story I could go into for a long time on that. But it's been a really neat project to do. And a lot of these ideas that we started to develop on surgical skill and structuring manipulation really are starting to have traction in the surgery field. Let me just quickly note that I haven't talked much about feedback. But I'll just quickly say we've been starting to look at ways to learn about how to give feedback to surgeons as well. We actually are using a crowdsourcing platform, again, to do this. The idea is to actually go back to that first video I showed you where I said, can you tell me who's better or worse? Well, you could do that pretty well, which means that people in Amazon Turk can do it pretty well as well. And so we've started to crowdsource a lot of our analytics for skill assessment. So just kind of too many numbers in this slide, but just quickly to tell you, turns out that we can get experts to assess skill, and they agree with each other about 88% of the time. A crowd, an Amazon Turk crowd, we can get up to about 81% agreement. And we can actually, from that, we can train classifiers for skill, basically comparative skill, that operate essentially at the same level as the crowds and the experts that we train from. And so we actually can build analytics around this that now actually, the idea behind this project is we're now starting to drill down to smaller and smaller chunks of the procedure, and we can say, where did you misperform? Where was the poor performance of skill? Yeah?
Just to check, each segment of the procedure is a binary classification, novice or expert?
Well, in this case, it's, so the whole idea behind this, I'm sorry, I'm kind of running through lots of stuff. The idea is to know, so early on I noticed that if you can do ordinal classifiers, if I can just do A is better than B, and I have a dictionary of performances, I can now grade someone simply by comparing them against the dictionary and determining what their percentile rank in the dictionary is. And so the way that we actually get grades out of this is we have a curated dictionary of performances. In this case, this is at the maneuver level. And so we can now classify them against all of these maneuvers, basically from 0 to 100, and we give them a percentile rank out of that just using the comparative classifier. Yeah?
How good is people's own classification on their own performance?
I'm sorry, how good are?
I'm thinking,
Oh, if you had...
doing the surgery yourself,
Mm-hmm.
if while you're doing it, you can classify whether you're doing well or not well.
So I don't know the answer to that. We actually do surveys of the residents and the attending saying, how well do you think this surgery went? But I don't off the top of my head know how well people's subjective performance is. I will say that if you ever care about getting a good surgery, and I think it goes a little bit to your point, if you're going to go in and you're going to have surgery, what you want to make sure of is that your surgeon slept the night before and that you have the second surgery of the day. Because the first surgery, they're warming up. The second surgery, they're pretty good. And then they actually decline after that. And if you go back, and we've done this for learning surgeons doing training tests, if you look at the learning curve, the biggest interrupter of the learning curve is whether or not how much they slept the night before. So a well-rested surgeon on the second surgery of the day is when you want to get any surgery done. And so I think, to go to your question, I think if you ask them about their self-assessment, a lot of it would be colored by these subjective factors, like, I felt tired and didn't feel with it or whatever, whether or not their technical skill was actually up there or not. The other thing, there's been some interesting data coming out. I should move on, but so one of the big questions, one of the things that's been driving training and surgery in the last couple of years is the fact that they limited the resident working week to 80 hours. So before that, residents would work 100, more than 100 hours a week occasionally. They would just be on call 24/7. And so they limited it to 80 because they thought this was a safety issue for patients. So they actually just have started to do some studies where they said, well, what if we don't do that? Does it actually change patient outcomes? And it turns out that patient outcomes don't change even when the residents work more hours. So even though they're more tired, there's some other compensatory mechanisms that apparently come into play that keep them from making too many mistakes because they're tired. Anyway, I'm sorry, that was an aside. So what I've done is I've kind of given you a sweep of this idea that I think more and more the technology is in place that we can take complex data, these manipulation tasks, we can structure it, we can actually start to perform assessments on it. And a lot of my group has been focusing on all of that problem. But what I'd like to do just in the last few minutes is kind of bring this back to robotics and say, well, what does this mean for robotics? How can we actually start to use it for robotics? Well, so I'll make three observations. The first is that in almost everything that I have done, we have pretty much been able to rely on the fact that we can take fairly complex manipulation tasks and we can break them down into fairly natural semantic units. And what I mean by this is when I go to a bunch of different people and I say, break this task up into pieces, they tend to break it up into roughly similar pieces. And in fact, we were just talking about the fact that just from the data itself, you start to see kind of natural discrete units emerge from the data. So even though we live in a continuous world, it's not unreasonable to think of having kind of natural basic units, vocabulary that you assemble to perform at least a certain range of tasks. As you gain skill, you evolve toward this common organized pattern of movement in terms of these units. And in fact, interestingly, we kind of have this innate ability to recognize that. Like you can tell an expert skier even if you don't ski, or you can tell an expert surgeon even if you don't do surgery. So there's kind of a natural efficiency that we start to recognize, which really is, if you think about mastery, this is kind of what you want to drive your robotic system toward. The other thing that we found is when you look at these procedures, some maneuvers, unsurprisingly, are much higher value than others, meaning there are some things that are easy to perform, some things that are very, very hard to perform. And it's the very, very hard ones that actually give an expert surgeon their expertise. And so there's kind of this focus point of saying, what are the hard things? And that's really what you want to learn. So just kind of, because I wanted to do a shout out, I'll say, this discrete representation has been recognized here too. So this is some work that a bunch of you, Ken, Peter, and company did here, breaking a task down into discrete units and showing that you could actually essentially develop an automated system using these discrete state changes in a learned representation for this little cutting task. I'm going to skip the failure modes. We did something similar, but we looked at it a little differently. We said, well, look, we've got all this data on these tasks. We can now learn these discrete models. We can get pretty good at it. Can we now, because we've got these high, low-value pieces, start to break the task down into things that can be automated and not automated, and essentially let the robot learn from data how to do the simple stuff? And so this was a paper we put out a few years ago with Nicolas Pedoy, where the idea was we just dump data in the top of this thing. It learns a discrete representation. Right now, the human is operating the robot manually, but it's able to recognize when that suture drive is done, the hard part that you saw at the beginning. It switches to automated mode and does the needle pass. And that's actually fairly easy for us to automate. We just basically learn a trajectory from the data. And then when it's done, it turns it back over to the human. So you're actually seeing a human-robot trade-off doing this task. And it's all learned from data. Like the only thing we did is at some point we clicked a couple of buttons that said this action, this action, and this action will be done by the robot, and the rest of the actions will be done by the human. Now, obviously, if we click the wrong buttons, it probably wouldn't suture very well. So it still requires us to know what parts we think can be learned from data. But it kind of illustrates, again, this idea that we're getting enough data, we can start to develop assistance from this data. And one other video, just to kind of go one level further, which is what you saw there was very much focused on what I'll call mimicry. So the next level we've been working on is to say, well, can I get more and more towards representing tasks in ways that generalize across situations? And so this is some recent work by my student, Chris Paxton. And it's now doing demonstration-based planning. So the idea here is that we've got a task that we want to perform. And we know that this task, again, can be broken down into discrete units. And we think of each discrete unit as essentially now being a set of demonstrations by an expert, as you saw. And now we want to perform it in a new environment. Well, we know the trajectories don't generalize. And so what Chris does is he builds a feature space that abstracts from the trajectory. So you can think intuitively of things like when you're doing suturing, you bring the needle in contact with tissue, then you drive the needle through the tissue, then you move another gripper close to it, and you pull it out. Well, there's a trajectory there, but there's also a set of object relationships that are taking place. And Chris basically develops a set of object relationships that represent a task. When we want to perform a task in a new environment, what we do now is well, OK, so first we train the robot to do things. So this is training, grabbing a link in a simulation. Let me just jump ahead here, if I can figure out how to do that. So now when we want to reproduce that trajectory, what you do is you simply sample to try to find trajectories in a new environment that have the same feature representation. So if the object moves, the configuration is different, it's still just trying to satisfy the same feature representation. Now, in this case, he's essentially optimizing serially. So he's doing each motion, then he's optimizing to get the next trajectory and put it down. You'll notice it doesn't work so well. And this is because he's doing serial optimization without any sort of a time horizon. So now what he's going to do is do the same task, but now he's actually sampling multiple actions ahead at the same time. And he's been developing a very efficient framework for doing this so that now each action essentially sets up the next action. So the neat thing about this is an expert does a demonstration. That demonstration basically becomes a sample for us. The sample really is the sequence of symbolic states or kind of discrete states that you have to go through. Each discrete state has a bag of demonstrations. We sample from that bag of demonstrations. We do that across multiple actions. And now we get a task representation that lets us generalize in a space where there are multiple obstacles. We can avoid different obstacles. It simply will choose different grasps from the bag of possibilities. And in fact, so those are the samples. So it's actually sampling trajectories. It's doing important sampling of trajectories as it goes along. And in fact, every time it does it correctly, it throws a sample back into the bag. So the more you do the same task over and over, in fact, the faster the sampling becomes because it's building up more and more successful examples of doing it. And so we're actually very close to that, building that little structure that we talked about, where literally the expert can demonstrate putting together the blocks, and the robot then can generalize that across building an entire structure out of those blocks. And in fact, we're going to the Hannover Messe in 3 weeks to demonstrate a robot that is going to build where somebody can essentially demonstrate building a structure to the robot out of these blocks, and the robot's supposed to be able to go back and build a similar structure in a different position with the object starting different points in time. So let me just kind of close by saying, so a lot of what I started out by saying I wanted to build a workshop assistant, and I've shown you a lot of the work that we've done over the last few years. On the perception side, now starting to structure the notion of what would it mean to be able to demonstrate to a robot a particular task and carry it out and do that relative to objects and kind of bring all that together. The question is, how do we get further than this? So the kind of canonical thing that happens to me is I give this talk and I show them the robot co-suturing with somebody, and they say, well, when will my surgeon be a robot? I don't know how many times I've gotten that question. And so I started to think about, well, what would it take to actually make a real robot surgeon? Like, what do we need to do? Well, you need to know a lot of stuff in the background. You need to be able to manipulate well, and you need to be able to understand the body. I think that's all things that kind of are in our grasp already. I think we'll be able to index all the procedure, all the information about anatomy. You'll be able to reinforce teaching suturing and that sort of thing. So the kind of very basic components are there. This notion of experience, we're already starting to see emerge. As systems go out into the real world, we're going to harvest more and more data. So, a car driving sees more and more traffic situations, and you have more and more data to learn from. But you notice that all of this is kind of undirected learning, if you will. And so I actually think the thing that's missing, and the thing that's most exciting to me, and what we're talking about the next level of learning for our systems towards mastery, is mentoring. And by that, what I mean is when a surgeon teaches surgery, they don't sit down and they don't perform an entire surgery to a resident and say, there it is. You've seen it. Go do it. Right? They go and they do a piece of it, and then the resident does a piece of it, and then they do a little more of it, and the resident does a little more of it, and they correct them, and they change them, and they give them feedback constantly to improve their skill. And that's an interactive process. That's question asking, that's directed action. And I think the only way we're going to see real mastery in these complex tasks is when we start to build these sorts of interactive systems. So our demonstration basis, for example, is kind of the beginning of that. But now we've got to have the robot actually realize it can't perform the action and say it needs more information, or a human to be able to watch it and correct it in different ways. So I'll kind of close with one example of how this sort of mentoring could happen. And I think it could actually be fairly behind the scenes. So this is a robot that's actually working in my house, and I'm trying to get it to take the laundry from my daughter's room down to the laundry. So you say, okay, go get the laundry from Sophie's room. So it goes to Sophie's room, and it asks, it queries the web for laundry, so cloud robotics at work. It gets back some pictures. And it says, okay, I'm in Sophie's room, but I don't see any washing machines, and there's nothing in my daughter's room that's folded. I know that. So I'm not going to see either of those. So then I say, it says, I don't know what you mean. So this is an opportunity for mentoring, right? This is like when the grad student comes to the professor and says, well, you said blah, 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 and I don't know what you mean. And the professor has to break it down into smaller chunks. So you break it down in smaller chunks. Take the laundry basket from the closet to the washroom. Well, this is a new query, but it's more specific. And laundry basket, gets back a query now that matches my daughter's clothes in the basket. And so it can actually then go and it can verify. So did I get the right thing? It can send me a picture and say, here's what I saw. And I say yes. And now suddenly it's gotten a little bit of extra information that it never had before. I broke a complex task into a simpler task, and I told it when it got it right. And of course, once it's done that, it can actually store that information. The dialogue can get shorter. And I think this is, to me, the most exciting part of robotics, when we start to interact with robots in this way, where it's really, we are teaching them, but we're teaching them in the same sort of interactive sense that we teach people. So let me just quickly then close by saying, suppose we do this, how would we know we were successful? So this is one of my goals. I want to instruct a robot with no more effort than a human. I want to teach a robot a task like I teach you. I want to be able to collaborate with robots in ways that are as good as collaborating with a human. So I can have a robot co-surgeon that's as good as a co-surgeon in the operating room. And lastly, I think ultimately, mastery is you can teach. And so I think when I get a robot that can actually teach me surgery, as well as a human can teach me surgery, that's really when we've successfully gotten robots that are able to master a task, when we start to learn from them, or people can learn from robots. So let me just stop there, in fact, and just say, this is, as I said at the beginning, kind of an arc of work. It's probably 15 years of different work that's been put together. But I think it's all leading in a common direction, and it's been a really neat team of students and colleagues that I've been able to work with while doing so. And with that, I'll stop, and if there's time, take a couple of questions. Thank you.